In this video, current electricity part 5, we'll study the meaning of the term internal resistance, the electromotive force of a cell, its terminal voltage, and we'll also proceed to derive a relation between the EMF E and the terminal voltage V. We know that every cell contains an electrolyte, the liquid which is or the chemical which is used to produce the potential difference, that is, which acts as source of energy provided by the cell for conversion to electrical energy. Whenever current flows through the cell, the electrolyte of the cell offers resistance because the ions have to move against the backdrop of other ions. Their collisions with each other provide the resistance, which is termed as internal resistance of the cell. So, internal resistance of a cell is the resistance offered by its electrolyte. We denote it by symbol small r. The EMF of a cell can be understood if we consider this circuit. We have the cell, a key which is open, that is, no current will flow through the circuit, and an external resistance which is load, to which the cell is supposed to supply the current. The EMF is the potential difference across the electrodes or the two plates of a cell in open circuit when no current is drawn from it. On the other hand, if you close the circuit, here see the second circuit, the key has been inserted and a current I is passed through this circuit. In this case, the potential difference across the plates of a cell or the electrodes of a cell is termed as terminal voltage or potential difference. It is the potential difference across the electrodes of a cell in a closed surface circuit. The EMF and potential difference both have volt as their SI unit because both measure the difference of potential. The EMF is greater than V, as we will see in a relation, because EMF is also termed as the maximum potential difference across the terminals of a cell when no current is drawn from the cell. Let's now proceed to obtain a relation between E and V. In this circuit, the EMF or the total potential difference which the cell can supply is E. Suppose this cell drives a current I through an external resistance R. The current also has to be passed through the cell. So, the internal resistance also opposes the flow of current. The total resistance in the circuit is capital R plus small r. As a result, if you apply Ohm's law, the current comes out to be I equal to potential difference E over capital R plus small r, the total resistance. Therefore, E equal to IR plus I into small r. IR is the potential difference across the resistance or across the cell in this closed circuit, and plus IR. This term IR, I into small r, is sometimes also termed as lost volts because this is a potential difference which is used to overcome the internal resistance. So, out of capital E, the EMF, I into small r is lost in internal resistance, and remaining I into capital R is useful and it provides current in the external circuit. So, V is less than E by a factor IR. Now, expression for internal resistance which will be useful for us, we have IR is equal to E minus V. So R is E minus V over I. Using Ohm's law here, I can be termed as V over R. So overall the relation is small r, the internal resistance, equal to E minus V over V into capital R. We will be needing this expression in later part of this lesson. Let us now reinforce what we have learned so far through this small part, reinforcing learning. We have studied a relation between EMF E, the terminal voltage V, the current I, and internal resistance R as E equal to V plus I into R. Remember, the term EMF is a misnomer, that is a wrong name, because the EMF or electromotive force is not a force. Its unit is not Newton, but it is work upon charge or potential difference, and the unit we know is volt. Let's proceed to solve a few problems to reinforce what we have learned. Question 1. A cell of EMF 2 volts and internal resistance 1 ohm supplies a current of 0.1 ampere in a circuit. Calculate the external resistance connected in the circuit. Here we have E is equal to 2 volts, small r is equal to 1 ohm, and the current drawn from the cell is 0.1 ampere. According to the relation I is equal to E over R plus R, we have R plus R equal to E over I, or capital R, the external resistance, equal to E over I minus small r. Substituting the values, you will get the result as 19 ohm. Question number 2. The graph between terminal voltage V and current I through the cell is as shown. From the graph, determine the EMF of the cell, the internal resistance. We have current plotted along x-axis and terminal voltage or potential difference across y-axis. We have to find the EMF. By definition, EMF is the potential difference when current is 0. So on the graph, spot I equal to 0 point and read the corresponding potential difference. It is 1.4 volt, which gives you the EMF of the cell. In order to solve this second part, that is calculation of internal resistance, we will use any prominent point in the graph. You may use A or B or C. For example, if you use A, V is 1.2 volts and the corresponding current is 0.04 ampere, which we have recorded here. V equal to 1.2 volt and I is equal to 0.04 ampere. You can calculate R by simple application of Ohm's law, V is equal to IR, and then use the relation R is equal to E minus V over V into capital R to get the internal resistance. In question 3, in the circuit shown, the charging of a cell is being done. You have E is equal to 5 volt and R is equal to 1 ohm for the cell. We are using a 10 volt source for charging and the charging current recommended is 1 ampere. You have to calculate the terminal voltage across the cell. Here, if you see the diagram carefully, this external source tries to drive the current here, because during charging the current must flow from positive to negative through the cell in opposite direction. So net voltage available will be 10 volts minus 5, because 10 volts is opposed by 5 volts. So that gives you E net equal to 5 volts. The internal resistance is 1 ohm and external is R. So I is equal to 5 over R plus R equal to 1 ampere. That is the recommended current. So using this relation, you can calculate capital R as 4 ohm. And then during charging of the cell, we have V greater than E, because the potential difference here must exceed 5 volts so that the current may flow in this direction from left to right. Therefore, the relation for V in this case will be E plus IR, or 6 volts, which exceeds E. So always remember, when you are using the cell, that is when we draw current from the cell, V is less than E, but when we charge the cell, V is always greater than E.